Okay, Algebra 2, this is the next notes lesson, which is homework 7. We are covering rational functions. So rational functions are just when you divide two things, okay, two algebraic expressions or two functions, all right, as you will see when we do some examples. So let me just give you a quick example. How about x squared minus 3 over x plus 1? All right, there's an example of an algebraic, a rational function, right? We've got a quadratic in the numerator, and we've got a linear function in the bottom. All right, so p of q and q of x are polynomials. All right, and q of x is not equal to 0 because, once again, we don't divide by 0, so don't let there be 0 in the bottom, basically. All right, so we're going to graph these things. All right, to graph these things, we're going to follow these steps. We're going to simplify the function. We're going to find the x-intercept by setting the numerator equal to 0. All right, because that's, if you remember, where the function's y value is equal to 0 is where the x-intercept is. All right, we're going to find the vertical asymptotes by setting the bottom equal to 0. All right, and then we're going to use these rules to determine the horizontal asymptotes. So if the degree, now degree, we're talking about the exponent. Okay, so if the exponent of the top p is greater than the exponent of the bottom, then there's no horizontal asymptote. All right. If the degree of the top is less than the degree of bottom, then the horizontal asymptote is the x-axis, which, if you recall, is just the line y equals 0, the function notation, or in our regular line form. Okay, the degree of p is equal to the degree of q, so this time the exponent in the top is equal to the exponent in the bottom. Then we're going to divide the leading coefficient. So the horizontal asymptote is equal to the division of the leading coefficient of the top divided by the leading coefficient of the bottom. All right, and then we're going to look for any holes, which we'll talk about next. So a hole is a point at which there's a break in the graph. Okay, so you're going to have a function like this, and there's going to be one point that's undefined. Okay, it's not an asymptote. The function doesn't approach it. An asymptote is when we have a vertical asymptote, for example. A function approaches it but never reaches it. All right. With a hole, we just have a break in the graph, and it comes from when there's the same factor on the top and the bottom, a common factor between the top and the bottom that cancels. Like, for example, in this function that we're going to do in a second, if we would have had x minus 2 here and then also x minus 2 in the denominator, those factors cancel, but they do create a hole, as we'll see. All right, and to find it, you can set the common factor equal to 0, so set this x minus 2 equal to 0 and solve for it, and plug it back in to find the y coordinate, which we'll do, and as we go through these examples in a second, it'll probably make more sense. So let's start doing some examples. So the first one we're going to do is this function here, x minus 4 over x plus 4. All right, we're going to identify all these things. Let's start with the x-intercept. The x-intercept is where, think about it, where it hits the x-axis is where y equals 0. So to find where y equals 0, we set the numerator equal to 0, right? Because if the top's 0, then the whole thing's 0. So where is the top 0? Add 4 to both sides, and you get x equals 4. So the x-intercept is at 4, comma, and if you plug in 4, you get 0 for y. So 1, 2, 3, 4. There's where it hits the x-axis. That's good to know. All right. The vertical asymptote now. These occur at setting the denominator equal to 0 up above, step 3 of our steps to graph. All right. So the vertical asymptote occurs where we set the bottom equal to 0, x plus 4 equals 0. All right. We subtract 4 from both sides, and we get x equals negative 4. So negative 1, 2, 3, 4. We have a dotted line there, and that is our vertical asymptote. All right, and we'll say that is x equals negative 4. Next is the horizontal asymptote. This is step 4 up above here. So we have the same degree. So we're in the last one when p equals q. We have the same degree or same exponent at the top and the bottom. So we're going to take a division of leading coefficients. The leading coefficients are the number that's in front of the x here. So this is a 1 and a 1. So it's going to be y equals 1. Y equals 1 over 1 is y equals 1. All right. Holes. Holes are common factors between the top and the bottom. There are no common factors between the top and the bottom, so there are no holes here. All right. Now the domain of this function, it might help to graph it, but basically we can stick in any number we want for x except for where the vertical asymptote is at x equals -4. So we're going to say all real numbers, but x cannot be -4, or if you guys like interval notation, that's -infinity all the way to -4, not including -4, as well as -4 to positive infinity. All right, and at this point we can graph the function. If you want to graph some other points, you can, but we've got a horizontal asymptote at y equals 1, which I never graphed. We've got a vertical asymptote at x equals -4, so we know the function must look like this, because it is a hyperbola, so it is going to alternate. Let's double check that on our calculator. So pull out your TI-84, or go to the website that Ms. Beguer shared where you can use this, or use Desmos. But we're going to type this in. So do alpha y equals to get that fraction after you hit y equals, and then do x minus 4, and then do x plus 4, and hit graph, and we should see the function that we graphed ourselves here. All right, they do alternate, hyperbolas do, and since we had a verified point here as the x-intercept, I knew that it had to go through that point and then alternate. All right, and the range then is all real numbers except for this horizontal asymptote at y equals 1, so all real numbers, y cannot be equal to 1, or in interval notation if you prefer, -infinity all the way to 1, not including 1, as well as 1 to positive infinity. Okay, let's just do a few more. We'll do number 3 here where the exponent's higher in the top than the bottom, and there's a hole for this one, and then we'll try one where the exponent's higher in the bottom than the top, and there's a hole for this one as well. Alright, so let's take a look at number 3. Let's try to factor this. This is a difference of 2 squares, so it does factor into x minus 1, x plus 1. Alright, so we do have now a factor that's the same, that would cancel. Alright, that's going to be our hole. So we might as well just fill that in right away. Our hole is at x equals 1. Alright, or if you want to put an ordered pair there, that's 1, comma, which is what I prefer you do. 1, comma, and then if you stick in 1, you get 2. So at 1, 2, you can tell that that is an issue, because in the original function, if you stuck in 1, right, you'd get 0 in the bottom, right, which is undefined. But in our new simplified function, if we were to cancel these factors, you'd get the point 1, 2. So basically what a hole is after you simplify, it's a point that is in discrepancy between the original function and your new simplified function, right? 1, 2 isn't really in this original function, it's undefined. But if we were to simplify it, now all of a sudden it's there. That's an issue, it's something we need to keep track of, and we call that a hole, all right? So let's go back through and find the x-intercept. The x-intercept is where we set the top equal to 0. So let's set x plus 1 equal to 0. So that is -1. X equals -1. And then plug that in for the y coordinate, and you get 0, obviously. So -1, 0 is where a function goes through. Okay, vertical asymptotes. These occur at zeros of the denominator. So, we would have a vertical asymptote at x equals 1, but it simplified it was a hole. So the vertical asymptote is there's none. Horizontal asymptote now keep in mind our function now is effectively x plus 1. Okay, that is our function. It's simplified, right? So that's just a line, right? There are no horizontal asymptotes. There are no vertical asymptotes. There's just this one hole. That's the only really issue. So the horizontal asymptote, we can say none. We got the hole. So we can graph this thing. It goes through 1, and it has a slope of 1, so it goes up like this. The only point that's an issue is this point 1, 2. 1, 2. This point right here is really not there. It's a hole. And we'll graph that in our calculator and take a look at that. But basically, the function's a line with a slope of 1, y-intercept of 1, with a hole right here. All right. So the domain is going to be all real numbers, but except for x can't be equal to 1 because that's our hole. And the range is all real numbers, except for y cannot be equal to 2 because that, once again, is our hole. So let's take a look and graph this function and see what the calculator tells us. It should tell us the same thing. So we go back to y equals, we hit alpha y equals fraction. We hit x squared minus 1 divided by x minus 1. And then we take, whoops, Made a mistake in the top. Let me fix that. So when we graph this, we should see the line, right? And we do. So we graph it, we get that line that we graphed. So we graphed it correctly. The only issue is there is a hole. This point at 1, if I hit second calculate value, all right, and I plug in 1 for x, I should get undefined, and I do. It's undefined there. Or if I look at my table and go to second table where it gives you all the ordered pairs of this function, there is an issue at 1. At 1, when you plug in 1 into this function, you get a 0 on the bottom, which is an error. All right, so this function is effectively this line x plus 1. All right, so this function is basically this line x plus 1 with one discrepancy, with one error, one hole at 1. So take a second and try to wrap your head around that. Maybe go through that example again, because it is hard to understand holes at first, but they're quite simple. They're just factors that cancel, and it makes sense when you look at the original function versus the simplified one.